In 1956, inside a University of Buffalo lab, an electrical engineer named Wilson Greatbatch was wiring together a new piece of medical hardware. His goal was entirely routine. He was building an oscillator circuit for a machine designed to sit quietly in a room and passively record the electrical activity of a human heart. He approached the problem as an engineer, analyzing frequencies and currents for a tool meant for data collection. He was trying to build a better way to listen to the muscle, not a way to fix it. He was constructing an observer. Within minutes, he would assemble a driver. At the time, doctors desperately needed this recording equipment to study the electrical signals behind cardiac arrhythmias. The heart's electrical system is governed by the sinoatrial node, the natural pacemaker. In heart block, this node fails to send the timing signal. Without that electrical cue, the muscle loses coordination, the rhythm breaks down, and the patient dies. In 1956, doctors had no mechanical treatment for heart block. They could record the data, but they could not restore the rhythm. Greatbatch was assembling his oscillator circuit when he reached into a parts box for a standard 10,000 ohm resistor. He pulled out a 1 mega-ohm resistor instead, a part with exactly 100 times the resistance he needed. He soldered it into the circuit without noticing the error. When he switched the machine on, it failed as a recorder. It was unable to receive any external signals. This oscilloscope shows what the circuit was doing instead. It was generating its own rhythmic electrical pulse, appearing as a steady green spike on the screen. These pulses were firing exactly 1.8 milliseconds apart. It was a repetitive, predictable signal. Greatbatch looked at the timing of that output. His knowledge of cardiac medicine allowed him to identify that specific frequency as the resting pace of a healthy human heart. He realized the circuit could perform the role of a damaged sinoatrial node. He had accidentally built an electronic timing signal that could drive a human heartbeat. Having the timing signal was only the first step. After his employer rejected the project, Greatbatch moved his work to a small workshop in a barn behind his house. He faced the massive engineering hurdle of miniaturization. He had to shrink a piece of desktop machinery down to a size that could fit safely inside a human chest. He also had to solve the problem of biocompatibility. The device needed to be hermetically sealed to survive the corrosive environment of warm bodily fluids. He spent the next 2 years working evenings and weekends, solving battery life and sealing issues one by one through trial and error. While the discovery of the signal was an accident, the creation of a functional, implantable pacemaker was the result of 2 years of deliberate engineering. In 1960, a device built on this design was successfully implanted into a human patient. The device worked flawlessly, providing the timing signal the patient's own heart could no longer produce and extending their life by 18 months. This chart tracks the impact of that design over the next 50 years. By 2011, over 600,000 of these devices were being implanted annually worldwide. This global industry, saving millions of lives, began with a single electronic resistor that cost less than $1. Greatbatch later reflected that his greatest breakthrough didn't come from correcting an error, but from the exact moment the wrong part went into the wrong slot and produced exactly the right result.